Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the NPTEL course on groundwater hydrology and management. This is week 4, lecture 4. In this week, we are continuing to discuss the important components of groundwater hydrology. And to continue our discussion, we will look at hydraulic conductivity, which is one of the most important parameters for groundwater hydrology. In the previous lecture, we discussed about the macroscopic view and the microscopic view of groundwater flow and how the water interacts and moves accordance to the material, the soil or the rock material. So in the macroscopic, or which is called the Darcian view, you have an average linear velocity of the water particles. Because in a discharge Q, which goes around a cross-section area A, the macroscopic view does not capture what is happening inside. So how does water move inside is not captured and not needed, to be honest, because in a macroscopic view, it is averaged. Okay, so you have an average linear velocity. So the velocity is assumed the same on the top, middle, and bottom portions of the soil. But in the real world, which is a microscopic view you see on the right-hand side, you understand that the water doesn't go in a straight line, as we see here in the macroscopic, and water would go in variable velocities along the soil medium. And this is because of the heterogeneous composition and arrangement of the soil particles. So you need to understand that there are microscopic differences and variable velocities. However, when you want to describe them in a particular equation, you need a macroscopic view. So that's what Darcy took over, and he modeled this groundwater flow through a pipe. So he didn't want to do it on the land and ground because of the microscopic variations. He did it in a lab setting. So Darcy found experimentally that the discharge Q, which goes into the soil medium, is proportional to the difference of the height of the water, H, which is the hydraulic head, and the difference we also call as gradient, between the ends, and inversely proportional to the flow length, which is the length of the soil column through which the water flows. So you have Q is directly proportional to HA minus HB. We will see what HA and HB is in the experimental setup. And Q is inversely proportional to the length of the soil column. Before that, just to introduce Darcy. Darcy was an engineer in France where he worked on fountains, water fountains, and he had to supply water through underground to make sure that the water fountains were working properly. For that, he didn't have any equation. This was very, very old times. And so what he did is he took the soil column to his lab and then did this equation. And till date, it is one of the most accurate, very simple, but most accurate description of the groundwater flow in a saturated system. Okay, the assumption is also that the soil inside is fully saturated. We need to understand Darcy's approach, because Darcy was doing this to send water into the fountain. And the fountain needed a continuous supply of water for which the soil and everything was saturated and through a pipe column. So we can look at the differences in his experimental setup and how he got it in this slide. So in the Darcy's experiment, what we notice is that The column of sand stoppered at each end. So either sand, soil, rocks, materials. The material, the matrix is kept in a tube and it is stoppered. A rubber stopper is put on the top and bottom. Okay. Water saturates the pores. Water is fully saturated inside the pore space. Now apply ourselves to the previous lectures. If we say porous space is fully filled with water, that means it is a saturated system. And also it means there's no air inside the soil. So this column of soil he took in a tube has full water inside along with the soil particles. How do you establish it? You just continue to pour water for a long time until the water comes out in the same rate. Okay, so Q is the input rate, and if the Q water comes out, that means it is saturated. Constant volumetric rate of inflow and outflow of water, Q. So he also maintained Q to be constant, coming in and coming out. And that is what was needed to operate the fountain systems. So he would send a known volume of water, which is Q, which is already measured and metered, through a soil column of length, del L, okay, or just L. And then he had a stopper and Q coming out. The cross section of the tube was measured as A, and he had 2 points of monitoring inside the tube, and those can be visualized as wells. Okay, so he wanted to know what is the flow inside the medium. Okay, so to understand the flow, he put 2 monitoring points, and between the points, he's going to calculate the well hydraulics and the hydrology, groundwater hydrology movement. So what he did is the first well is called well A, let's say A, and then the well B is in a lower elevation. And why does water move from top to bottom? Because water flows from high potential to low potential. There's no other fancy instruments here. It's just a Q he is sending in. He doesn't have to push it because gravity is pulling the water from high potential to low potential. So when you put in the well, automatically the water level in the well will equilibrate based on the atmospheric pressure. The pressure inside should balance the pressure outside, and it falls into a particular level after it equilibrates. And that is HA, we saw in the previous equation. HB is the same water level measured in the well B. Okay, so del H, or the hydraulic gradient, it would be your difference in the H and divided by the length, del L. Okay, so what we have here is a distance between the wells and also a difference in the head. Also, what we need is the elevation of the well inlet from the datum, which is 0. So he had the table as 0, and from there, how much is the elevation of hydraulic head 1, which is HA, and hydraulic head B, which is at HB. So he measured the elevation of the well Z1 and Z2. Then he measured the total hydraulic head, which is H2 and H1. So H2 and H1 are going from the datum, which is the 0 elevation. So from the 0 elevation, you go up to the water level. This includes the elevation of the well. Okay, the elevation of the well is the point at which the well opening is there from the ground, which is 0. And the hydraulic head is, on addition to that, the water column height is added. So now we have the total potential. Okay, so H1 is higher than H2, and that is why groundwater will flow from H1 to H2, because high potential, low potential. Okay, so it flows from high potential to low potential. So Q is given as the volumetric flow rate, A is the cross-sectional area, H is the hydraulic head, which is including the elevation, okay, elevation of the well from the ground, and L is position coordinate in flow direction. Okay, so how much in the flow direction at length. Okay, So Darcy's law is given as the first law. What it says, it is proportional to the hydraulic head difference, which is del H. Del H is the difference between H2, H1 and H2. Okay. And also proportional to the cross-sectional area, directly proportional. It is inversely proportional to the length between the wells, between the estimation points. So now any proportionality can be converted to an equation by introducing a proportionality constant, right? So this proportionality symbol would go to an equal when we introduce a proportionality constant, and that constant is called hydraulic head conductivity. Okay, so the hydraulic conductivity is given as K, and A is the area del H by del L. So if you take the area out, I'm not interested in the total volume, but I want the velocity or the discharge. And that discharge Q is rated by the area. So if you divide by area on both sides, you get small q, which is equal to minus K dH by dL. Okay, so this is a very simple equation, but captures the flow of water between two wells and also the discharge rate. Now let's take a step backwards. Why do we have a minus? Where did the minus sign come? Right. So when we discuss, it is like, okay, it is proportional and it is inversely proportional to the length. But where did the minus sign come? The minus sign is introduced by Darcy to document that the flow is in the reducing direction of potential. So the negative is a directional value, not a value that you put on discharge. You cannot minus the discharge. Okay, so what do you mean by minus discharge? There's nothing as minus discharge, but the negative sign indicates that the flow is in the direction of reducing head. Okay, so it flows from high head to low head, and that needs to be captured. Otherwise, how do you know which side is the water flowing, right? So to document that, Darcy had introduced a minus sign, and it flows from high potential to low potential or towards the decreasing head. The head is decreasing. So all of this is captured in a very, very simple equation. And to be honest, working with groundwater systems for the last 10 to 15 years, I've noticed that this equation has been most powerful, even compared to the newer equations that come now and then. So there's not much additions done to this equation. And all these groundwater models are based on this equation for saturated flow. These equations and descriptions can be taken from Fries and Cherry book, 1979. As I said, it is one of the very important books that a groundwater hydrologist would have. And all these government schemes are also referring to these books. Flow is in the direction of decreasing head. So the negative sign, please understand, it is a direction value, not a value that you put on the quantity. It is not a decreasing discharge, minus discharge plus discharge. It is the direction. Flow is in the direction of decreasing head. Also understand the difference between a large Q and small q. Large Q is the flow, which is a volume, and Q meter cube or L times 3 on the power. But your small q is a rate, a velocity kind of thing. So it is a discharge and L by T. So the time would come in this equation. Whereas in the discharge, it is volume per unit time. Moving on, we have a horizontal pipe filled with sand to demonstrate Darcy's experiment. In a different book, I've taken a different approach to just show the same explanation, but in a more different way than the Darcy's book. So horizontal pipe filled with sand. So there it was slanting, but here it is an horizontal pipe. to demonstrate Darcy's experiment. So as the book says, it is originally vertically or slanted position, but we can also explain it in a horizontal way. Why do we need to explain it in a horizontal way? Is to capture the ground system. Most of our ground is not going to be always like this in the field. Okay, so for example, in a rural area, you want to monitor the groundwater flow between two blocks. And the blocks are going to be straight. It's not going to be like tilted, etc. But inside the ground, it may be tilted. And that is because of the layering. You remember the aquifers we talked about? So the layers might be tilted or different, and that causes the head difference. So what this diagram says is that there are two wells, and two wells have different hydraulic head. So HA is the hydraulic head on well A, and HB is the hydraulic head on level B, well B. We cannot ask why is one higher than the other. It could be different aquifers. It could be different pumping regimes. So even though it's horizontal, the levels are different. Now, the L is taken as the difference between the wells, right? And so the basic equation is Q is equals to minus K, hydraulic conductivity, A, which is the cross-sectional area, times DH by DL. DH is your change in the head or difference between the head from HA minus and HB, and your DL is the distance between the wells. Now, this DH by DL is called the hydraulic gradient. And what you also notice is that K, the property K, is the one which captures the property of the soil, because area A is basically the area of the cross section. H is the hydraulic head, which is a water property, and del L is the difference between the wells. So where does the property of the soil or the solid come? It comes in K, hydraulic conductivity. So the conductivity, as I mentioned in the previous class, is a term given to the soil and how easy it conducts or lets the water to pass through. And so we call it hydraulic conductivity, which is a property or a function of the soil. Moving on, please understand there are lots and lots of units for this values. It can be expressed as gallons per day per feet square or meters per day. It's all in a L by T dimension, which is length by time. So if you divide the gallons, which is a volumetric term, by area, you get one length, and the day is your time. So you can have multiple units. So please be careful with the units. I recently was in an examination where the student was trying to say, no, it doesn't agree. The data doesn't agree. But then the simple thing was that the units were different. So make sure the units are captured correctly. I'm going to stress this again and again. Please make sure what the unit is and see if it is agreeing when you compare. Okay, so let's look at some of the hydraulic conductivities. In the previous lectures, we looked at permeability, porosity differences, and now hydraulic conductivity. If you look at it, hydraulic conductivity is a function or can be expressed as a permeability and along with gravity constant and your viscosity and your density of the fluid. So it is basically a related variable. So for clay, it is very slow, centimeters per second. So think about 10 minus 9 centimeters per second is the flow rate kind of velocity of water in clay, or how clay allows water to flow. So it's very slow. So when you go to a field, the first question you can ask is what type of soil it is. And if they say clay, then you would understand that a groundwater recharge would take long time. We'll have some examples in the next class. So moving on, silt and sandy silts, the mixture of clay, sand, and particles have a slightly reduced hydraulic negativity or a higher hydraulic conductivity because sand actually can improve the hydraulic conductivity. So then when you go to silty sand and fine sand, you have more hydraulic conductivity. So we're going in increasing hydraulic conductivity. Okay. And then when you go to well sorted sands, glacial outwash, which is the deposit by snow melt, and well sorted is that the particles are well sorted, good space in between, then your hydraulic conductivity increases. So the highest would be, at least on this data set, it is the well sorted gravel. Gravels are bigger in grain size, and they have good built structure because it is well sorted, and it has space in between. So when you sort something, it will have a lot of space in between, and that space can make the medium conductive, and that conductive will increase the hydraulic conductivity of the material. So you would see higher water flowing through recharge and groundwater discharge through well sorted gravel, and the least in clay. Clay also swells. It also takes the water and holds on to it. So all this is kind of captured by your hydraulic conductivity. We can also use a Freeze and Cherries book that we used in the previous lectures for permeability. Let's take an example of, again, the silty sand, because that equates to your fractured igneous metamorphic rocks. If you go back to the class notes, you understand that is the dominant aquifer system in India. The hard rock aquifer covers more than 60% area. And so if you take that, we're going to take that as an example to understand hydraulic. We'll use a centimeter per second or meter per second to discuss the results. So you see that it is anywhere between 10 minus 4 to 10 minus 3 centimeters per second. It's very slow, whereas in your aquifers, alluvial aquifers, which is around 30% in the country, the Ganges, Indus, Brahmaputra, the Kaveri Delta, so those regions will have a higher hydraulic conductivity. So those would be more on your permeable basalt or your clean sand, the sand, alluvial sand. And then you could see it jumps up. The hydraulic conductivity can jump up from 10 power minus 4 to 10 power minus 1. If I draw a line here, it is 10 power minus 1 centimeters per second. So it is moving at 1 millimeter per second, which is pretty fast. Okay, so you're thinking about per second, okay, per day. So then you convert it to per hour, per day, per year. Always go in time in sequence. We'll do some calculations in the next class to show what does these value mean. Okay, but before that, I would like to also introduce the hydraulic head concept in this lecture. So always note the ranges. The range is big. And why is the range big? For example, in silty sand, the range is from 10 power minus 5 to 10 power minus 1. So minus 10 power minus 4 orders of difference. And that is because of the mixture, the combination of your silty sand could be different, and also the management of the land could be different. But either way, it falls within this band. Also note that when I just take one value, let's say 10 power minus 4, it could be a clean sand on the border of clean sand. It could be a silty sand. It could be a silt loess or a glacial till. All these 4 or 5 different types can be within that one value. So it is up to you to understand first what that material is by physical and lab estimations, and then you pick your hydraulic conductivity. Water levels. This is a very, very important concept to understand the hydraulic conductivity and groundwater hydrology, because that is what we are measuring. Okay, at the end of the day, the government and the system would measure water levels, and I'm taking a small example, just an introduction. We will jump into one lecture on this data to understand this. So all this data would convert to a groundwater hydrology equation by the examples we showed in Darcy. So this is a picture of the groundwater data that is calculated and captured by the government of Tamil Nadu, and on your right is the Central Groundwater Board. So there are two agencies, at least in Tamil Nadu, collecting groundwater data. So they collect the data and then they collect it in different years and months, and then they equate the difference to understand what is happening. So before that, let's get into the hydraulic head concept. I've already explained this in the Darcy equation, but let's take one well to show how do you calculate the elevation. Because in the real world, the zero is not the table, because the real zero is your center of your location where the level is zero. So normally the zero is taken as the sea level. On the planet, the elevation zero is taken as mean sea level. Okay, so where the sea is starting, that is called zero, and from there the elevation can go up or down. Okay, so let's take z as zero, which is your sea level. We are somewhere in let's say Chennai, and I'm on the beach. That level, the water level is zero, and I'm moving inward into Chennai to measure the groundwater level. I need to measure the water level, the hydraulic head, and from the hydraulic head, I will go to Q, which is your Darcy's equation. Okay, so I go to a well, and the first thing you would notice is that the elevation of the well is not there. You cannot have the elevation of the well readily, the hydraulic head readily calculated. So you need to calculate. The first step you do is to ask what is the depth of the well and where the well is actually open for measurement. So here is the point of measurement. And as usual, as I showed in the previous slide, you would measure the water level or depth to the water. So you end up calculating this. So you have one value, which is the depth of the well. And also you have your water level, which is psi. Okay. And what is needed for your Q is H. How do you calculate H? You ask for the elevation of your ground surface at that point, which you can take from topographic maps or digital elevation maps. So you have the elevation of this your ground, which is 1. Okay. Now 2, you have this Z, okay, which is your point depth, basically your depth of your well, which is 2. And you know your psi. How much is your psi, which is the water level, which is 3. But how do you get at 2? How do you know how much is my elevation from the ground? You know from the depth of the well, which is this, you know, okay, this is your 2. And but you won't know this one because you have to calculate this indirectly. Okay, so you know 1, you know 2, and 3. How do you get at H? By subtracting 2 from 1, you get this area, this length. Okay, so you get this length when you subtract 2 from 1. So 1 minus 2 is going to give you your Z. Okay, and you know psi, which is your 3. So Z plus your 3 will give your Z plus your 3 will give you your H. And that's simple. Please understand that this is what we want, but in order to get this, you have to subtract your elevation using your depth to the well. Okay, so now you get H. You do this to another well. So I walk to another groundwater well and I do another H. I know the distance between the wells, and then I would do the equation as Q is equal to your minus hydraulic conductivity. So since I am in the field, I would ask what type of soil it is, and then I know the hydraulic conductivity from the values I showed from Freeze and Cherry book. I know the, let's not do the area of your well. So let's do your Q, small q. Okay, so we don't need the area of cross section. We just need the discharge velocity. So let's say Q is equal to minus K times your DH, which is your distance, the difference between your hydraulic heads by the length, DL, the distance between your wells. So all this we have done just by calculating two values, which is your elevation of the well and then the depth to the well to get at your Z, which is the elevation of the well, from the measuring point. Then we measured the groundwater level to get at 3. 1 minus 2 got me Z, and Z plus 3 gives you H. Okay. So with this, we would calculate the groundwater hydraulic head for one well. We do it for two wells, and then we establish the equation, Darcy's equation. But remember, we need the hydraulic conductivity, which can be obtained from the previous values which are shown here. So always have this. You can have this slide. I use this slide always to measure all the materials are there. So to any system in the world you want, and take a government report to understand what is that particular soil, and then go to this slide and get the value, and you can put it here by measuring the ground surface, the elevation of the Z, which you get by subtracting the groundwater well elevation or the depth of the well, and you get Q. So please note that we will also look at some Q values in the next lecture. Thank you.